So now we're starting to kind of inch our way towards the idea of motors. And what we're going to look at now is we're going to look at what if we apply a current to a loop like this. And we're going to have magnetic field lines kind of running this way. Okay, so if the current goes around this direction, we're going to have a current going up like this, a current going like this. We're also going to have a current going down like this, and we'll also have currents going this way on those little pieces. Now, applying the right-hand rule, if the current is going north along here, and the magnetic field is going along this way right here, then with the right-hand rule, we should be having a magnetic force pushing out like this. So that B represents the force of magnetism. Likewise, on the other side, if you use the right-hand rule, you're going to have force of magnetism pushing this part of the wire towards us, out of the paper. Now, you might remember that back here, if you look at any kind of current that's running parallel to the magnetic field lines, it's not going to have any effect. And so what we have here is we have this pushing this way, this pushing this way, and we're going to see a rotational effect. So this is rotational motion. So remember that torque, tau, is the same as force times the length from the pivot point or the fulcrum. And so what we're going to do here is we're going to assume that the loop is an L by L square, and we're going to figure out the amount of torque based on the magnetic field. So we're going to look at the different torques of both sides and add them together. So we'll call this side over here force 1 and this side force 2. Now force 1 is going to have a torque if you multiply by the length it is from the center here. But the center here is going to be half of L, so we're going to write this as L over 2. Now if you add that to the other torque, which is rotating in the same clockwise direction, that would be the second force times the same length divided by 2, because it's half the length the other way from the pivot. Okay, so really this is the same as 2F1 L over 2. Because they're going to have the same exact force, you can kind of just shrink it down to one force, F1, and then 2 over 2 is going to cancel, so the torque is going to be the force basically of magnetism times L, the length of one of the sides of the squares of this loop. Now if I substitute in the magnetic field created by a current, it's going to be ILB times L. And so really the torque created is going to be current times L squared times B, and a lot of people will just take this L squared, and since it's a square, that's really just the area of the square. So the torque is going to be based off of the area of the loop times the magnetic field strength times the amount of current going through it. Also, if it's at an angle, because it's going to rotate a little bit and then eventually be at an angle, you can figure out the amount of torque by putting sine of theta in there. So let's look at an example here. Let's say that we have a loop, 10 loops of wire. And so part of this is to explain what happens with more loops. We have 10 loops of wire. It's going to be 0.1 square meters. It's going to have a current of 1.5 amps. And we're going to say that the field strength is about a refrigerator magnet. So it's going to be 5 milliteslas. We want to basically know how much torque we're going to get out of that kind of circuit loop. And this is going to be the maximum torque. So this is if we lay the loop perfectly perpendicular to the magnetic field lines, because as this loop rotates, magnetic field does not act on it as much. So one thing we need to make sure we know is that actually there's another way to, another thing with torque, and that's you can do a number of loops, and the more loops you have, the stronger the torque. So the way I think of it is, well, the torque, if you just keep adding loops, it's just kind of like you're multiplying the number of torques going on there, so you just multiply by n. So in this case, we're going to have 10 loops. The current is 1.5 amps. The area is 0.1 square meters, and then the field strength is 5 times 10 to the negative 3. I'm getting an answer of 0.0075 Newton meters. Now Newton meters is the unit for torque, and so you could use that to figure out, well, if I have this amount of torque rotating on there, you could figure out how much force by figuring out how far away in meters the force you want to apply is. So for example, if I was exactly 1 meter away, the force would be 0.0075 Newton meters divided by 1, which would still be 0.0075. So this is a pretty weak force, but remember, if you got really close to where the radius is, you're going to have a larger and larger force based on the torque, because your torque is going to apply more force if you're closer to the fulcrum. Anyway, the details are that you need to be able to find the torque.